everyone. Welcome to Apex, the more you know. I'm Ashley, the app scientist, and today we're going to integrate your data. Why? To determine the intensities of your reflections. How can we do that? Let's zoom into my screen and I'll show you.
After you collect your data frames, go to Reduce Data and Integrate Images. Your unit cell will be shown on the top right. Click on Import Runs from Experiment to populate the table. If you are no longer connected to the instrument or have imported your data to another computer, you can choose Find Runs, and this will open a window and allow you to choose which runs you want to integrate. The top right lists the unit cell that you will be using to integrate. If you had multiple unit cells you were trying, make sure you select the one you want to use with the drop-down menu. The resolution limit at the top right is the global resolution limit. A typical resolution limit for molybdenum sources is 0.7 or 0.75. For silver, this value can be much lower depending on how far out your sample diffracts. For copper, make sure you get data to at least 0.83. If possible, try to get data to 0.8. The first column of each row tells you the name of the first image in a run. The second column lists how many images are in that run. If you wish to cut that run to integrate only the first 150 images out of the full 180 images, then you can change this number to 150. If you don't remember what the total number is, you can always right-click on the number of that row and say Count Images, and this will update to the total number in that run. The third column allows you to cut the resolution of a single run. This value will be used for this run instead of the global resolution limit that we have listed at the top. The final column lists what the name of the output file will be, and also where that will be saved. If you wish to change the location or name of all of the output files, click on the top left square between the tiles for the columns and the numbers of the rows. This will select all of the rows and columns. Then, right-click on one of the numbers of the rows. Now you can choose to either change the output directory, or the folder where the newly created files will be saved, or you can change the output base name, or the name of the files. For example, right now the output base name for each run is just the sample name, chloropropam, but I might want to name them chloropropam_ortho-P, so that I can remember that I've integrated this one as orthorhombic P. You can also change the output base name for just one of the runs. For example, this run is the fast scan that I ran to determine my unit cell. Instead of having it called run 1A, I can rename it to be called unit cell because that's how I determined my unit cell. Click on Start Integration. Now, the software will go through each of your frames, find your reflections, and integrate the area of those reflections to find both your intensities and also your sigmas, or standard deviations, of these intensities. We are going to keep an eye on these plots. You want the spot shape correlation, over here, to be high and flat, just like this. And you want your spot shape profile to be a nice and round green ball. This program, also called SAINT, uses 3D data integration algorithms to learn the spot profiles of the strong reflections, which helps to better extract intensities from weak reflections using least squares fit. The correlation coefficient indicates how well the current learned profile matches new profiles being added. A high correlation suggests very good data quality. Since this integration goes by so quickly, sometimes I want to go back and look at each run individually. You can do that over here on the top right of the panel where it says Integration Finished. Click on that drop-down menu to see each pass and integration for every scan. Each scan undergoes at least 3 passes that looks at the first few images to get an idea of how best to treat the reflections. You will notice that for each new pass, the average correlation coefficient gets slightly improved, and the spot shape profile starts to be a fully encapsulated sphere where none of the edges are cut off. This is because when each reflection is being integrated, there needs to be a predefined box to try and encapsulate the entire reflection, and some of the background to determine the background. If some of the edges of the reflections are cut off, your intensities will not be completely accurate, and neither will your background. Each pass is adjusting this box size to accurately accommodate the size of the reflections in your experiment. Once you get to the integration step, done with the passes, this is done with the final box size and should have the best average correlation coefficient and spot shape profile. This is completed for each scan. There are other statistics that you might want to see plotted. This list here provides you with the opportunity to view these plots. Just go ahead and click on the check mark and watch your plot appear. Once you are done here, click on Close. To view the output text file from each of the scans' integration, you can click on the output file name and select the LS button to view the LS file for the integration of this one scan. But if you want to see the file with all of your scans integrations merged together, you need to see the 0MLS for merged. Click on Sample and then Browse Work Directory. This will open your work folder for this sample. Near the top of the most recently created files is your _0m._ls file, the merge list for all of your integrated scans. If you open this in a text editor like Notepad, you can get an overview of your integration. Something I like to check here is a number of spots exceeding the frame Q size, especially compared to the number of total spots predicted. Here, out of almost 150,000 reflections, we only have 99 reflections exceeding the Q size. This is not very many, so I am not concerned. But if you had a large portion of your reflections being rejected due to the Q size, you would want to make an adjustment to grab more of your reflections. I'll show you how to do that. Back in the Integrate Images plugin, on the bottom right, click on Integration Options. Here you will see a whole list of options, and even a button to see more options. What we would want to adjust here to have a bigger Q size is right here, the Active Image Q half width. The default is 7. This is mostly fantastic, but for some samples, like proteins and large porous molecules, you may need to increase this number a bit. Now, keep in mind that this is the half width. What that means is when a reflection is found, the program will look at 7 frames before that reflection and 7 frames after, which means that we're really looking at 15 total frames to try and get a whole picture of a reflection coming in and out of reflection conditions. If you increase this value to 8, you will increase the total number of frames viewed to 17. Okay. Another place where adjustments can be made is the Refinement Options window. Here, you can make adjustments to your initial box size. This is that box we talked about earlier that is trying to encompass a reflection without cutting off any edges. If you are working with moths or other samples with streaky reflections, it might be worth it to start off with a larger box size. I usually start by doubling the initial X and Y sizes. You do not need to make modifications to the Z value. Now you can click Start Integration again to reintegrate your data with this updated information. Sometimes you might find that your initial unit cell from your unit cell scan was slightly off from your overall data collection. If you want to rerun your integration with updated cell information, you can go to Sample, Import, P4P, and choose the newest 0m.p4p. Click OK. This will update your unit cell to the more refined values determined from your previous integration. Click Start Integration to reintegrate. You will be warned that you will be saving over your old integration files. This is fine. You might notice that the initial scan passes are much better this time than before. This is because we are using that updated information. Looks great.
What a quick process for all that computation. Looks like you're ready for scaling and absorption corrections. Are you ready to experience the benefits of Apex for yourself? You can go to brukersupport.com to upgrade. New user? You can request a demo license and see how Apex can transform your lab's workflow. Thank you for tuning in to this episode of Apex, The More You Know, where we determine the intensities of your reflections. Join me, Ashley the App Scientist, next time for more exciting crystallography. Until then, happy refining.